We're working basically to look for ways to make mesh communication and mesh networks a viable alternative to centralized networks. And so I'll start by talking a little bit about mesh networks generally and what we do there, and then get into the Lot49 proposal and explain some of the choices we made and hopefully get some feedback from you all about that. So mesh, the idea to start with here is that that the internet is designed to be a decentralized network, but yet it's run on centralized connectivity. So even though we're usually talking about it in a decentralized way, the actual connection is not decentralized. You can think of this as actually very great because you can send an SMS or you can FaceTime with somebody in New York, you can FaceTime with somebody in Hong Kong, and this goes like magic that this happens. And it's going to go to your local tower, it's going to go to some undersea cables, your data is going to hit another mobile mesh network and come back to somebody else's mobile phone. That's pretty amazing. But if you do the same thing in the same neighborhood, you're going to go through the same infrastructure. You're going to go to a mobile tower, you're going to go through backhaul cables, through a bunch of servers, and then out again to somebody else's mobile phone. And this isn't really efficient, but this is how the system is designed. Even when you're sending an SMS to somebody right there, right next to you. And the ironic thing is that your phone is actually capable of communicating in a two-directional way with phones nearby, but it's almost purposely built to not allow you to communicate. The system is designed for you to be a consumer of connectivity, but not a provider of connectivity. And there's some different reasons for that. That's sort of what it's saying here. So you can plug into connectivity, but you can't provide it. And this is actually for various economic reasons, because your ISPs don't really have an economic reason to allow you to communicate without going through them. So no device is built that way, and no business model sort of takes that into consideration. And even protocols like Bitcoin that rely on a decentralized network are, at the end of the day, just overlay mesh network or overlay P2P networks on this centralized infrastructure, which is really controlled by a small number of very centralized organizations. And in some countries, it may only be one organization that runs the whole infrastructure for communication. And the big problem with centralization is resiliency. And when I say resiliency, I don't just mean in the case of a storm like they had in Puerto Rico, which is a good example, but also resiliency against attacks that could be more political in nature. So censorship, that's something that we've seen in Hong Kong and other countries from time to time. And also sort of resiliency against attacks of your privacy. That's another important thing, that when all the data is being funneled to a centralized place, that's a really convenient place for that information to be tapped, for metadata to be monitored. We know from Edward Snowden that this actually does happen, not just in China, but everywhere. So there's a lot of reasons to want decentralized communication. So this is a GoTenna. This is a device that basically pairs with your mobile phone to allow you to communicate over a decentralized mesh network in a totally off-grid manner, without Wi-Fi, without satellites. And it communicates with via your cell phone, so it basically allows you to do free messaging, and it does end-to-end encryption. It uses the UHF band, and it's a transport layer that will work essentially when your centralized networks don't, when they don't work. And this was originally kind of inspired by the power outages they had after Hurricane Sandy, when even in a highly connected place like Manhattan, people couldn't communicate. And what you get from a mesh network based on this kind of technology is a bottom-up network for communication, so that you can take sort of the density of people using it and turn that into capacity for the network. And the way that works is a message sender, so the message sender there in the corner, if they want to communicate with the destination up here, they're going to send their message over the radio in sort of an omnidirectional way until they reach the relay there in the middle. And then the relay is going to then broadcast again, and then until it reaches the destination. And all of this is basically handled by routing protocols that are built into the devices. And if those of you, I'm going to get into like Lightning Network, but those of you that are familiar with the Lightning Network know that part of the challenge of any sort of a P2P network is routing in an efficient way. And with a mesh device, that's even more important because you're not just worried about bandwidth, which is rather limited, but power. You don't want to, if you're in a mobile device, you also have to conserve power. So the Gotenna people, one thing they really optimize for is making a very efficient routing protocol that also is efficient from a power standpoint. So nodes don't drain their battery basically unnecessarily to rebroadcast for other people. So the real challenge is not as much the technology. This could work, and has been capable, something that could work for a long time. But how do we incentivize people to participate in these networks? And there's a series of challenges that all mobile mesh networks have had to deal with. The first and the most important is zero start. So it's the same problem that any P2P network has. So whether it's BitTorrent or Bitcoin, if you're the only one using it, the value is not there. So you have to find a way to bootstrap the network so that people will start to use it. The other is coverage. You want as many people as possible to use the network so that a message can get from A to B. Because if you've got gaps in your network, or if you don't have anybody, if you've got people running it but not near you, then it's not going to be an effective mesh network. And capacity, where there is demand, so where there's a lot of people who need it, or where there's a particular bridge where there's a lot of demand, you would like people to fill that gap, to be incentivized. Now, if you're dealing with a centralized system, they just top-down decide where things should go, where your base stations could go. But a mesh network, especially what we're looking at here is a decentralized mesh network. There is no central planner, so this all has to be an emergent property of the network. Power is unique for a mobile network, so maybe BitTorrent doesn't have a problem with the power of your computer, but you do have to be conservative with the power drain that you're going to impose on people who might be reeling for others they don't necessarily know. So in a purely altruistic system, people might have sort of battery anxiety, and that's something you'd like to avoid and incentivize people to do it anyway. And spectrum is also sort of a unique one. You would, if you're a central cell phone carrier, you bid hundreds of millions, billions of dollars for spectrum. But how can you create a financial incentive for the people who are deciding, which are regulators and government, to allocate spectrum to peer-to-peer mesh networks? Right now, it's a pretty paltry allocation. So that would be something, to make mesh successful, you would want to get better spectrum and have more of it. And then this is more of a challenge. A local versus global is a challenge for mesh networks. And I'll get more into it, but it's the idea of the fact that you're off-grid, that you're not always going to be directly connected to the internet. It creates challenges for verifying payments, for example, or verifying incentives, whatever incentives you use. And that's a little bit analogous to the problem of running off-grid Bitcoin, which some people are working on, but that's something that's a big challenge for doing incentives over mesh. Let's see. Oh, I skipped my slide, sorry. That was this one. The local versus global, what that actually is about is you might have a local network, you might have New York fully networked, but how do you get to London? You do need certain nodes that are special that basically can act as a gateway and bridge connected areas over great distances or through through different technology than you might have for your actual local mesh. So Daniela Perdomo, the co-founder of Gotenna, she looked at Bitcoin and she looked at distributed cryptocurrencies and thought, there's something, they've managed to bootstrap their own use through their protocol, and was very interested as early as 2017 of what lessons can we take away from cryptocurrency to look at how we could incentivize the use of mesh networks. And if you start in a sort of a naive way and you just look at Bitcoin, there are some pretty clear incentives. There's the miners have incentives. They get a reward for mining. They get transaction fees for mining. And the users have a sound money. They have a non-inflationary, censorship-resistant money. So that's their incentive to use it. But those aren't easy to map onto a mesh network. So instead, we looked at the Lightning Network. The Lightning Network is a much closer analog to what we're doing from the beginning, and has a system in place for incentivizing nodes to relay, in the Lightning Network's case, payments for other people. So they're going to, your Lightning node analogy is that instead of data, you're relaying payments, but you're still supplying coverage in a sense and capacity by doing that. So the mapping goes like this. So instead of transferring value, you're incentivizing the relay of messages. And the model that we're proposing, so you can see instead of sending value here, there's Bitcoin, we're additionally sending a message. So the nodes are still getting paid as they would in a set by sending payments, but they're only the sort of the release of the pre-image, as you will, like the secret that releases those payments is going to be tied to the message received on the other end. So that's, from a high level, how we're sort of adapting the Lightning Network. And if you look at other systems like Blockstream's BlockSat API, they also use Lightning payments to bridge data over their satellites. So that shows you how this also sort of maps into a system that allows you to incentivize gateways. So not just mesh nodes within a local mesh, but you can also use it to incentivize gateways who can collect perhaps a larger payment for bridging these long distances. So the protocol that we're working on, we call it Lot49, and the name is inspired by a Thomas Pynchon novel about a mysterious underground postal delivery service. If anybody's read that book, so that's sort of where we get our inspiration. And in the Lot49, so nodes are going to establish payment channels instead of with anybody in the internet. It's going to establish payment channels with their local mesh, the local within radio distance, basically, nodes that they can communicate with. So that's one way we're going to differ from a Lightning network. And then we're also going to have some nodes that are gateways to the internet, and those gateways are going to be the ones that are responsible for communicating with some node who's on the internet who can do the sort of heavy lifting of the blockchain as far as confirming payments, because we're not expecting, at least in this initial version, we're not expecting all nodes on the mesh to have a complete map of the blockchain at all times. So we're relying on what we call witness nodes. You could sort of think of them as like a block explorer that you ask for, in a sort of trustless or trust minimized way to confirm transactions and to put them on the blockchain, going through a gateway. So the key here is that we're going to try to do Lightning, but we're going to try to do it in a way that ruthlessly minimizes the bandwidth and communication between nodes. That's a primary feature of what we're working on here. So that primarily to update payments, because that's what you do mostly in the Lightning network, is two nodes communicate to update their state. So to try to really ruthlessly optimize that, and also when you do have to communicate with the internet to either set up a channel or to close a channel, that's another case where it has to go through multiple hops, and you want to also very much reduce the bandwidth required for that. And the way this might interact with Lightning is that you could still have the Lightning LN penalty links on the internet, but then you could also have nodes that run both. They would both run sort of a Lot49 variant of Bitcoin and the LN penalty and be a gateway between those two networks. So we're really looking for an interoperability at the blockchain level, but at the messaging layer, they could be very different. So that to do a lot of what we're proposing in Lot49, we're proposing two soft forks, or we're proposing to rely on two soft forks that are being talked about right now. One is L2, which would rely on the SIG hash no input or any previous out Taproot variant. And also MuSig, which is part of the Taproot BIP, and would give us Schnorr signatures. And I'll get a little bit into that next. So this is just a high-level view of L2. And the key thing for us that we think helps us with bandwidth is that when one node updates the next node in the chain, when they update the state with their channel partner, they can actually, it's a symmetric update. So there's a symmetric update, unlike LN penalty, where both nodes basically have to sign sort of an asymmetric set of transactions to make that a valid update. And by having this symmetry, it's really just the payer who has to sign a transaction to the payee. And the payee can just hold on to that transaction. They don't have to send a signature back to the payer, because if they ever want to drop that on the blockchain, they have everything they need now to confirm that transaction if they have to arbitrate that through the blockchain. So that's a pretty important consideration for us. And having that feature of the symmetry and the single sort of what we call simplex payment channels It also means that your lighthouses, so your off-chain or your on-chain or like internet-connected nodes who are acting as lighthouses, they only need to keep a single transaction. And maybe you're even using mesh nodes that are low-powered, so they would only have sort of a single transaction that they need to manage to basically keep that channel information current. And also not having the revocation. So there's a revocation transaction and information that has to be exchanged as you invalidate old states. That's just another piece of data that we can avoid by doing it in this L2 manner. So we think it's a pretty dramatic way to reduce the bandwidth. And we're dealing with, even though we could theoretically do this over high bandwidth communications, we're really focused on the lowest bandwidth. So this would be things like long-range mesh radio or satellite communications, things with really low bandwidth. So anything we can do helps. So the second thing I mentioned was multi-signatures, so something like music. And where that helps us, as I mentioned earlier, is in the cases where you do need to send a transaction to the blockchain, you're going to have to relay it through multiple mesh relays and then through a gateway. So anything we can do to turn basically two signatures, the normal 2 of 2, you have two signatures, into a single signature, gets us potentially a 50% decrease in the bandwidth that has to overall go over the network. And in the case of music, if you only got 2 nodes, you can negotiate for 96 bytes of signature, which is the biggest part of most of these communications. You can communicate a single 64-byte signature. And if you didn't do that, then you would have to send 2 64-bit signatures to basically confirm a multi-signature update. So it may not seem like much because 64, 128, but this is a significant fraction of the packets basically that we're sending. So it is useful to consider. We're doing other things that are also done in Lightning, but just doing it in a more aggressive way. So Lightning already does things where they infer the transaction. They're not like literally serializing the transaction and sending it over the wire. They're just sending the parts that are different, like the signature or the amount or the destination. So that's information that we can infer, and we can go further. We can basically make our templates even more constrained. So, for instance, you could have save bits and bytes by having just a limited number of relay fees, for example, that you support. So that's one way. Things like public keys. This is also done in Lightning. You can use the XPub system, so that using HD wallet deterministic public keys, you don't have to send the entire public key. You can send some sort of key that you can use to derive it. Another thing that just some brainstorming we've had is you could potentially use smaller locks. So right now they send a 32-byte secret. You could send a smaller one. Sorry, you could use something like a RipMD 160. That would require a feature bit in Lightning, so that would be a little more contentious. But it's just a way that we could try to minimize the data. And part of the reason that works is we're looking at lower value payments. We're not looking at even $10 payments, because this would be like what you would spend for sending an SMS, something like of that size. So the data should be, the prices should be very like minimal micropayment sized. So we can maybe make some sort of trade-offs with security for low value. The other way, and this is actually a pretty significant way it's different, is routing. So a big amount of data that's generated on the Lightning Network is just routing messages, just gossiping about who your peers are and how to get to them. And there's a lot of work being done to make that more efficient, but that's something that we wouldn't necessarily bring over to the mesh network. We have mesh routing protocols. I mentioned this Aspen Grove, for example, used by Dotena, which is optimized for the mesh system to be very low bandwidth, low power, etc. And so that no gossip protocol is one way we can reduce the amount of data. Another way is take out the onions. I mean, there's another trade-off. So we're making a lot of trade-offs, but the trade-off with removing the onion system is privacy. But using a mesh network, you gain a certain level of privacy already, because if you're doing Lightning over the internet, your IP is going to be tied to your payments, essentially. If you didn't have the onion system, then somebody who's observing the network could sort of tie you to the payments you make. But in the mesh system, it's an omnidirectional radio. So you've got a certain level of anonymity just physically from the fact that you're doing a radio broadcast. And then additionally, if you've got an ISP or you've got a mobile phone, then there's a hardware identifier that's also tied to your payments. But with something like this sort of mesh system, you can change your ID, so once a day, once a week, whenever you want. So you don't have to have a persistent identity with your hardware device. And that's another way that you can get some of the same benefits you would normally get from an onion routing system, but without the bandwidth. Because 1.3 kilobytes per onion is actually, for a low bandwidth network, would be over what you have, basically. So that's not possible. And there are other general issues of different ways you can do this. So one issue that when you look at payments is you could amortize. So if I'm sending 6 messages, I could do 1 payment and send 6 messages. So these are variables you can play with. There's trade-offs if you do that, like if you do 1 payment for 6 messages and the person in the middle moved, then the relays wouldn't, the final message wouldn't be paid for. So this is where you just have to look at the topology of the network and figure out how much change there is in the topology. And if it's a pretty when the network is static, you could send a lot of data for a single payment, and that's a way to amortize your overhead, the overhead needed for incentives over more data, essentially. Another problem that comes up basically in any situation like this is the fair exchange problem. And what this means is when you send a message to somebody in this system, it's going to eventually reach the destination. And that destination, in the Lightning Network, they're getting a payment. So they have a strong incentive to drop that either to return the pre-image or to drop it onto the blockchain so they get paid. But here, the values will be sort of de minimis values. They won't be the major motivation. The major motivation will be the data. So if your final node is in somehow collaboration with the sender, they could just take the data, take whatever message they got, and not continue to relay the pre-image that's necessary for the relays to get paid. We don't think this is a terribly bad problem because you can do it. You can fix this in sort of other ways with local blacklists and things like that. But it is a problem that there might be some smart solutions to. And then probably the final one that's really important, and I think there's a lot of work in the Bitcoin space looking at this, is how do you minimize offline transaction verification? So this would be similar to your light wallet situation where you might have a wallet that you might have a mobile node that doesn't have the full blockchain. How do you keep them up to date and able to confirm transactions without bringing in the full blockchain every 10 minutes or getting an update every 10 minutes? So, did I miss one? No. So, just some final thoughts to think. Like I said, we're looking for feedback. So this is the kind of things we're looking for feedback on: is ideas about how do you. Well, let me start again. Sorry. So, an important difference with the Lightning Network is the difference between the bandwidth, and how do you. We're not interested in for Lightning, you're looking at how much value you can transfer through the network. Here, we're looking for how much data you can transfer through the network. So any overhead used to make incentive payments to relay nodes is going to come out of the bandwidth that you have available to send data. So that's an overriding consideration for us. And kind of corollary to that is that signatures and public keys are the part that's the long pole in the tent. You can't reduce the signature, you can't compress it. Public keys, we have some ways to work around, but especially signatures. Anything we can do to use a different signature scheme or to more efficiently use signatures, that really helps reduce the amount of bandwidth used for the incentives. And then how we can use off-grid nodes in an efficient, trust-minimized way. That's also, it's similar, like I said, to the light client problem, but we would have that even more, we would be even more dramatic for us because you might have mesh nodes that don't have internet connectivity in any sort of regular basis. Some of this you can do with timeouts, you can sort of scale things, but if there's smart ways to do that we're really interested. So yeah, this is the slide I was looking for. So the future, some things we're looking at to help with some of these problems. So we're very much at the beginning of this, but once we get sort of the basic Lightning idea implemented, we're going to look at some of these ideas like channel factories and state chains. That would be a way for nodes not to have to go to the blockchain when they're establishing channels with other nodes. So they could go back to, say, a channel factory and open up new pairwise connections. And that would be a nice way to decrease the reliance on having an on-grid gateway connection. And then just off-grid blockchain sync. If you could do it in a very efficient, bandwidth-efficient way, keeping nodes in sync with the full blockchain, I mean, that would be cool. So Erlay, for example, that would be something we're thinking about. And then there's things like UTXO inclusion proofs. This is something that I think Peter Todd has looked at and others, and there may be some ways to do this with Utrixo. It would be a way to keep a very small version of the blockchain UTXO set on the devices and keep them updated. But there's usually trade-offs with bandwidth, so that's still pretty speculative. Another thing we've looked at and sort of have walked away from, but would still be open to if it were helpful, would be doing something like short aggregate signatures. So there's like BLS signatures. It's something that probably will never come to Bitcoin, but if there was some way to do that in a way, to use them in a way that wouldn't need to be confirmed on the blockchain, you know, that's something that we would be interested in as well. So again, I'll just reiterate, we're looking for ideas. You know, we've got a lot of opportunity for cryptographers, for game theorists, for people who are looking at basically ways to make Bitcoin more efficient on the blockchain. A lot of those ideas translate over to making it more efficient in bandwidth. So please share your ideas if you have it. We have an open source proposal on the web here. So it's an open source white paper, and we also have some simulations. You can talk to Jonathan over there. He's working on our simulations. So if you want to look at the code he's working on, that's get some good ideas there. And that's it. Thank you very much. If anybody's got any questions, this is where we'll be drinking beer. But any questions? Yeah.
Can you do a quick ELI 5 just about how the Gotenna technology works? You said it doesn't use satellites. You didn't talk too much about it.
Sure. I can tell you more about that. So this is a radio, and it's going to pair with your mobile phone, and then it broadcasts over this UHF band. And then any radio within range will pick that up, and if it's the final destination, fine, it gets the message. Otherwise, it's going to relay it using this Aspen Grove routing protocol to find a final destination. And it'll hop over many hops until it gets to that destination. So in a nutshell, that's sort of what it's doing. But we're looking at sort of SMSs, so a lot of people confuse it and think it's somehow doing internet over the radio. It isn't. It's really doing more like, think of it like SMS or API data. So that's the level of communication that you really get from something like this.
Does it have the ability to do BLE? Bluetooth Low Energy?
Yeah, I believe that's how it talks to your phone.
Gotcha. So
BLE4, I think.
Have you guys looked at doing smaller mesh networks with, for example, a community of Raspberry Pis?
Yeah, well, you could, if you mean, well, so you can actually pair this over Bluetooth with your phone or over USB with a Raspberry Pi. So we actually have an open SDK. So Gotenna, anybody can basically can download the SDK and create apps for the Raspberry Pi or anything that runs Python. And we've done that. So I didn't talk about it, but we have an application that sends Bitcoin transactions over the mesh until it gets to an internet gateway, and that'll run on your mobile phone, but it'll also work on Raspberry Pi. We did some fun stuff with a BlockSat too. So,
yeah. You mentioned like routing is often the hard part. I imagine like when you first get started, it's kind of expensive to find a route to the internet. So I'm wondering how does that work in terms of you paying? Do you pay as you discover it, or could you explain that?
That's a good question. I mean, so they have this. If we use the Aspen Grove system, the idea there is that it's zero overhead. So as you send messages, you're also exploring the network. And probably in our conception of this, there would be messages that are sent for free and messages that aren't sent for free. So you probably would start by sending messages that were free, and they would just maybe have more delay. But with sending those messages and also other messages routing through you, you would gain value that you could use to route your own messages. So I think they call it a vector routing, something like that. So you don't necessarily have to know the exact destination. So other people discover the route near you, and then then when you send to them, they sort of send it the rest of the way. I'm not describing that very well, but I think the network topology sort of grows as you stay on the network. So, but if you want more details, I can point you to some papers that describe it. Anybody else?
Yeah, is it one HTLC by packet right now? Is the current?
One HTLC? Yes, that's the idea.
Doesn't scale, I think, from the Lightning Network.
Why is that?
I mean, let's assume every array node has a communication channel with a witness, right?
Okay.
I think.
Oh, no, it wouldn't be with the witness. It would be with their local nodes nearby. So that if you've
Yeah,
got...
but stroke a gateway or, I mean, because even if you want to run Lightning in its current form, run on the internet, right? So you
Yeah.
need to have a Lightning node connected to the internet, right?
Right.
And I mean, you're just going, if you send one HTLC by packet,
Yeah.
so I think the current HTLC on one transaction right now is something like 483, right? So
Bytes.
you need to settle them quicker than you send 483 packets on your machine.
I don't quite follow you there. I mean, we would be looking for lower bandwidth. That part of the...
No, it's
No.
more latency.
No.
I mean,
Oh, latency.
Latency.
Okay. I'll have to talk about that later. I don't quite understand, but it's...
I mean,
And then the other thing that I did mention here is the idea if you can amortize. It might be one payment for 6 packets. I mean, that's a parameter that
I mean,
you'll have to discover.
I'm quite sure you need to aggregate a lot of packets with every packet is redeeming a secret and aggregating them in a bigger HTLC.
Yeah.
Scale.
I mean, the reason I think about it as one packet per HTLC is you might be sending a single message. You might just be sending, I'm sending an SMS to you. That would be one HTLC per message. But
Great.
doesn't seem great. Yeah, well, I think if we can get the overhead low, that's what we're aiming for.
I don't completely understand how it would break, but I guess one of the things I'm wondering is like, if you had these channels open, Lightning channels, if somebody chose to like cut connectivity to you, they'd be in a position to sort of, they could close out at maybe a state where you would be in a good place.
Yeah, sure. I mean, that's a danger for Lightning, and
Okay.
this model too. But any model where you're disconnected from the blockchain,
Right.
you're
It seems like
at
you're
risk.
just especially exposed when you're like not on the internet. I guess I was wondering if there's like, I imagine watchtowers would help this, but you might not be.
Yeah.
So I was
I mean,
wondering if this is-
mobile phones in Lightning have that problem, like if they go offline for a period of time. So you'd have to scale your timeouts appropriately, or have watchtowers that can help you with that. And watchtowers might not even be online watchtowers. It could be mesh watchtowers that are just monitoring for you. So so there's a lot of things that are not quite specified, but that's a direction we would probably go for that.
So in that scenario, do you guys model the Go antenna users as stationary or moving? Like as
Moving, I mean, there's probably going to be both. There's probably going to be mobile users would be sort of the hardest case, but then you're going to probably have fixed gateways, and some people will just set up in places where they can relay data for profit, say, and they may be plugged in, but the target user would be a mobile user.
What's your project this summer, and how does it sort of relate and play together? with
Good
this?
question. I can go back a slide here. So I'm working on L2. I love L2. What's not to love about L2, right? Where is it? Anyway, it's not too laggy there. But so I'm basically trying to take the L2 paper and specify it and create a test driver that can just test the theory and practice of how L2 might work. And that would be just as a sort of first step to trying to create an L2-based test net. And then from there, we can try to integrate it into some of this mesh stuff. So that's the plan.
Can you tell me a little bit more about GoTap? What kind of range does that little thing?
So that's a good question. So it has, I think online on the website, they say 4 miles range. So 4 miles in line of sight, and potentially a lot further actually. But if you're down in the concrete jungle here, you won't get 4 miles because it doesn't go through walls and it's going to bounce around. I think in like a suburban environment, I get like 1.6 kilometers, something like that. But it varies, and we have some users who use it in, like I was saying earlier, ultralight gliders, so they're up in the sky, and they get many more miles than 4 miles. So it just varies. And I think this is just one implementation of a radio technology. There's other radio technologies And I think this is part of the idea of spectrum. If you can really create a use for it, better spectrum will become available. And that's but you've got to bootstrap a network for that to be something that would be considered.
Are gateways like the same device, or it's a different like class of device?
Yeah, people have taken these apart and put bigger batteries and bigger antennas to run a gateway, but you wouldn't necessarily have to. The key with a gateway is just that if you had this paired to a cell phone that also has a mobile data connection, that would be a gateway, because it's just bridging between mobile and internet, like wired internet. Do you have a question, Alec?
Yeah, can you make this send only? Like, could you use this to broadcast Bitcoin transaction from an air-gapped computer without making it vulnerable to the internet?
Yes. We actually, if you go online, there's something called TX10, and that's exactly what that does. In fact,
it uses that to send only and not receive anything.
Yes. Yeah. In fact, we would like to add receiving. That would be pretty cool, but right now we don't have that working. But what we do have working is you can have this via the USB connection I mentioned, hooked up to your air-gapped computer that's receiving blockchain information from the BlockSat. So you can actually receive BlockSat data, so you're completely air-gapped, so you can receive transactions and you can send transactions.
Although the second you receive, you're not air-gapped anymore.
Well, you're sort of. It's still only one directional from the satellite. I guess they could give you some poison over the satellite. That's possible. But you'd have to be pretty paranoid for that.
You can have a virus inside a Bitcoin block.
Yeah, that's possible. Someday we'll see that, I'm sure. Any other questions? Yeah.
What is the source of the spectrum band that you're using and its width? Maybe this is a stupid question, but is this sort of like public use bandwidth that you're sending these signals across?
It's the UHF band, and it's I think it's unlicensed spectrum. So it's the same that you use to open your garage door. So something, I think it's, for those, I'm not a real RF engineer, but I want to say it's
868 to 915 in the US, I think.
okay. Yeah, and it does vary. Yeah, okay. For those RF people out there. Anyone else? And I'm going to try to give a demo after we're done here. If somebody wants to see it in action, see what mesh. Maybe if we get ambitious, we'll try to send a Bitcoin. Not a whole Bitcoin. You can send less. That'll motivate people to test it, though, if I do. Great. Thanks, everyone.